Hello everybody and welcome back to Environmental Science 101. Here we get to nitrogen and our nitrogen cycle. So this is going to be one of two nutrient cycles that we're going to talk about here, right? So all animals, all life is going to need not just energy that it gets from food, but nutrients as well, all these other things. Now, when we think of nutrients, we think about nutrients that we as human beings maybe get from food, right? Things like carbohydrates, fats, minerals, proteins, right? And what we're really getting out of these stuff are these more basic things, right? Or more basic building blocks or elements or components, including carbon and nitrogen, among many others, right? But we're going to focus on those two because those two play a big importance in our ecological systems, not just with human beings. So, nutrients, right, is going to be our big term, all those chemical elements and compounds which organisms need. They need energy, they need nutrients. Now, I've committed sort of mortal sin with this, right, which is kind of combining animals and plants together, but carbon, nitrogen, hydrogen, oxygen, right, C, N, H, and O, going to be like 95% of what's going on with organics, be really important for us to remember. Secondary in terms of importance of our nutrients, although these are really elements that we're naming here. Phosphorus, sulfur, and calcium. Now, do we need to sit down and memorize this list? No, but it might be good whenever we see nutrients as we go, right, and throughout the course, to think back to this and think, okay, was that one of the most important? Was it one of the secondary? Or is it something that's going to be far less important, right? Are vitamins, minerals, tertiary stuff that maybe could be built out of these other things, but it's still important. So the source of these, right, is going to depend on how we get our food, right? So for a producer, we're a plant, we're going to get this stuff from the soil primarily. If we are consumers, we are going to get this from the stuff that we eat, right? So the plant gets it from the soil, and then the animals get it from the plants, or the consumers, right, get it from the other animals. And then finally, detritivores and decomposers are going to get this from dead and decaying stuff. For the most part, though, we're going to be focused on our producers. So let's talk about nitrogen a little bit as an element. Seventh element, surprisingly hard to get a good photo of this stuff because it is a colorless, odorless gas that doesn't react with anything. It makes up about 80% of our atmosphere. About 20% of it is nitrogen, and then about 1% is going to be all these others, inert gases for the most part, and some carbon dioxide. It's going to be here on our periodic table. It is a non-metal. It is a gas at room temperature, forms these molecules, which we'll talk about in a moment. And this is going to be required for all life of any form, with no exceptions as far as I'm aware, maybe send me one. So there's a problem though with this, right? Okay, so this nitrogen that is in the atmosphere is in a form where it is essentially locked away. It is in the form of molecular nitrogen, which is triple bonded, right? So we might remember, right, more bonds are going to be harder to break. You got to put more energy in order to break them. And a triple bond is going to be 100 times harder to break than a double or single bond. Vastly harder. So here's our problem, right? All life depends on plants. We established this with our trophic levels, right, is where the energy comes into the system. Plants need tons of nitrogen. They need a lot of it. Nitrogen in the air has these strong bonds, which are really hard for us to break, right? And the plants can't just get nitrogen out of the air. There's got to be these other steps along the way. So then where do they get it? And the answer is going to come from looking at our nitrogen cycle, right? So nitrogen is going to come in a lot of forms. At first, it's maybe going to seem a little bit overwhelming, but over time, we'll be able to make sense of this and cluster it in a way that makes sense, right? So we got our molecular nitrogen in the atmosphere, right? It's our big reservoir, right? Atmosphere is big, holding tons of nitrogen, but in this unusable form, so much of it. And it's also going to have these different forms inside of the soil. We have ammonia, right? We have ammonium, nitrates, nitrites, and these are going to correspond to things with our chemical formulas over here. Now, I left off these two. We might remember nitric oxide and nitrous oxide. These are, for the most part, pollutants. We don't want these in the air. Usually come from human sources, especially combustion, right, and making fuel into energy. Nitrous oxide also is going to be used medically. If we've heard of laughing gas, that's what this is made out of, right? We're going to be focused on these forms in the soil. So the two that plants really want, right, that they want to pull out, that's freely available for them, are going to be ammonia and nitrates. Now, could they use nitrites in some of the others? They could, but it's not preferred, right? It's not the best food for them. Where is this stuff going to come from? So the ammonium is going to come from animal waste and organism decay and get turned into these other forms. Our nitrate is going to be an intermediate step, and there will be a graphic to put this all together in a moment. Our nitrates are going to get eaten by plants, and then there is also going to be this process called nitrification, which we just need to know is where soil bacteria are going to take nitrogen that is in these other forms and put it back into the atmosphere, where it can be used again, right? Okay, so let's keep this in mind moving to the next section. Plants like nitrogen, which is fixed, and by fixed we mean made into a form that's easy for them to access, like with nitrates and ammonia. Nitrogen fixing is going to be this process of taking atmospheric nitrogen, which is hard and locked away, and turning it into an easy form. And for the most part, this is going to be done by bacteria. Now, it can be done by lightning, typically to a much lower degree, and it can actually come from fertilizers. This is the reason why we need to fertilize, is make sure we have enough nitrogen. We're going to hold off on this for now, right? Okay, so we're taking nitrogen gas, which is unusable, and putting it into a more usable form for our plants, nitrates or ammonia. For the most part, this is going to be done by soil bacteria, but a little bit by lightning. And one example, right, of a nitrogen fixing bacteria, right, is going to come from our legumes. Now, you might remember when we talked about mutualism, this mutually beneficial relationship, it's going to come back here. So we have got nitrogen fixing plants, right? So they have bacteria in their roots that is going to fix nitrogen forms so that the plants around them can use them. Although that's not necessarily why the legume does it, right? The legume, as we talked about, gets something out of the deal, right? It gets all the nitrogen it needs. The bacteria and fungi down there get protection, right? Now, legumes are going to be important when we talk about crops, right? And planting food for agriculture, right? So we can imagine, right, if we used a bunch of other plants, right, and we didn't really care about the amount of nitrogen in the ground, that we could use it up, right? And we could deplete it over time, right? Taking out ammonia and the nitrates that are in that good form until we're left with severely depleted soil, at which point we got to put a lot of fertilizer in there, right? That's one way to do it, which is going to have a lot of bad side effects. Or we can look at other ways like legumes, which are going to be much more productive. And we could also think about a certain example, right, where we have used legumes in order to support the nitrogen needs of other plants without having to continuously add fertilizer. Maybe we've seen that before. And as a fun fact, when we eat them, they tend to be high in protein in large part because they got so much nitrogen available to them. Legumes, if we need something to picture in our heads, right? Beans are going to be legumes. Peas, including things like chickpeas. Broad group that's going to contain many types of foods, and good for you too. Cool. So we can start to put this together. This is not quite our full nitrogen cycle. It's more of a simple nitrogen cycle, but it's going to work for us. Okay, we've got in our minds this pond, and it's got fish, and it's got water plants in there. So what's going to happen? The fish are going to eat the plants, right? And they're going to do what fish do, which is poop, right? They produce waste. That waste is going to have ammonia. It's also going to have ammonium, which is going to be transferred by bacteria into a more usable form. That bacteria is going to turn the ammonia into nitrates and nitrites. Nitrates being really good for our plants to use. The plants take these up, use it as nutrients, right? And then the fish eats the plants. If there's excess nitrates, then the bacteria in there is going to go through that process of nitrification we mentioned and return it to the atmosphere as molecular hydrogen. So in a more visual form, right? We've got our fish, right? It's going to eat plants. It's going to produce waste, right? Especially ammonia. This is going to get turned into nitrite, which we don't really need to worry about. It's just one of our intermediate forms. It's going to be processed by bacteria again into nitrates, which are then going to go back into the plants, which are going to be eaten by the fish. Okay, we can see how, so long as things are in the proper balance, this is self-sustaining. Now, I did steal this graphic from Petco, which is why they talk about removing excess nitrates through water changes. This doesn't always have to be done, especially if you have enough algae plants, right? If they take up enough of those nitrates, then we're not going to have excess nitrates or nitrites. And we will be testing for these whenever we go to do water chemistry. So maybe we can directly measure the level of these things as well. Awesome. So now we get to move from our more limited nitrogen cycle to the whole thing. Now, I don't love diagrams like this. They are busy and I feel overwhelmed when I look at them, but we're going to put it all together here and go through it, make it work. So we start, right? We've got nitrogen in the atmosphere that gets fixed, turned into a usable form, which plants like, right? By these nitrogen fixing bacteria. Now, NH3 is ammonia. This is going to get turned into nitrites, or as an intermediate step on the way to nitrates, which get eaten by the plants, right? The plants are going to feed animals who decompose into ammonium, which gets turned into our intermediate step and into nitrates, which our plants like. Now, if we have excess, especially of nitrates in the soil, sometimes these get, through this process of denitrification, turned into nitrogen in the atmosphere. Now, do we need to remember every single term here? No. Do we need to remember the broad strokes and maybe at least be able to go through the logic surrounding this? Yes, that is going to be important. We don't necessarily need these terms, but it is important for us to understand the concepts, even if we don't get there with the chemistry. I did want to talk about one last idea to cap off our section, and that is this thing called the Haber process. So this, right, we have molecular hydrogen, nitrogen, we have molecular nitrogen and molecular hydrogen, both, right, in gaseous form. And essentially what this process does is it turns them into NH3, which is our ammonia, right, which is a form that plants like, right. This is one of those scientific discoveries or inventions that radically reshaped the world whenever it was discovered, right. So essentially this is human manufacturing of ammonia, which is really going to be fertilizer, right? Developed back in about 1910, right? So this would have been pre-war by a German chemist. I think it's Fritz Haber is the name. Yes, so this can be used to make fertilizer, and it has been used as fertilizer and fed billions upon billions of people through this process, right? It is good to make food and feed people. It is good that we know how to do this. At the same time, this process can be used to make explosives and was used to make explosives for the German military. So we are responsible for feeding billions, but can be used in many ways, right? We'll leave it at that. The science is clear. What human beings do with the science is sometimes less clear. This is also among the most studied chemical reactions in the world. If we ever take a chemistry class or look into that subject more, you're going to be studying this, guarantee it. So we use this to make fertilizer in the form of ammonia, and lots of it, in order to put things in a nitrogen form that plants need. Okay, awesome. Next we do our carbon cycle to follow it up.